Hello everyone, I'm Moumita Tabassum. I'm a PhD student in the Department of Computer Science at the University of Alabama. I'm glad to present my work on designing accessible block languages to support the inclusion of students with and without visual impairment. Before I jump into my real work, I would like to give a brief introduction about the block-based languages and challenges for visually impaired and blind learners. The interest in computational thinking and computer science education has increased greatly over the past decade, particularly in K-12 context. Learners as early at an age of 4 have been seen to understand basic programming concepts and successfully solve simple programming projects. Early awareness and equal access to computer science and programming courses can instill a computational mindset and skills that are helpful in post-secondary and future career opportunities. There are two types of programming languages. I think we all know about the text-based programming languages such as C, Python, Java. Another type of languages are block-based languages that has recently become a popular way to introduce coding among young children and is considered as a stepping stone towards the traditional text-based programming languages. In block-based languages such as Blockly, Scratch, or Snap, programs are created by dragging and dropping blocks. These blocks resemble puzzle pieces that can be sequenced and add together. One of the benefits of blocks languages is that it does not require complex syntax or vocabularies to be memorized and depend on recognition instead of recall. Uh, Large vocabulary of text-based programming languages often makes learning difficult for novice programmers. Also, the blocks-based environment allow blocks to be joined with other blocks only when the syntax is valid, which can eliminate common syntactical errors. And the appealing visual metaphors makes the learning interesting for young children. Anyway, all of the advantages of the blocks-based languages that I mentioned are mainly applicable for sighted students. What about students with visual impairment, those who won't be able to rely on their vision for learning programming? According to the ACS 2017, approximately 568,000 children have visual disability in the United States. Another study shows that among the visual impaired students, 63,000 are elementary or primary school going children. So, a huge number of learners can be deprived of the benefits of learning blocks-based languages. Therefore, learning programming can be a great barrier for them. Very few blocks-based programming languages and environments provide accessibility support for visually impaired and blind students. However, these environments are not generally used by sighted children because of their limited design possibilities. There are no such blocks-based environment that fits both students with and without visual impairment and blindness. Also, most of the existing accessible blocks-based environment requires use of expensive tangible user interface for providing accessibility or platform-specific device that may not be available widely. So the necessities for a universal and accessible blocks-based environment to provide the foundational concepts of programming to children with and without visual impairment serves as the motivation behind our project. The target age of users are 6 to 8 grade. A web browser-based environment with not needing to use any robot or other tangible device will be easily available and affordable, as well as the same environment for both sighted and visually impaired students might boost the social confidence for students with VIB. So to implement the design of an environment with all these features, we created a blocks-based tool called Grid World. To build the tool, we used the Blockly library that has been developed by Google and MIT. It is highly customizable and extensible. Different popular blocks-based visual programming languages and editors have been created using Blockly. Here in the picture, you can see a prototype of the Grid World. The Grid World has been designed with all the traditional features found in the most blocks languages, such as executable world, palettes of blocks, code workspace area. The purpose of the environment is to provide students with a fun context for understanding the core programming concepts such as sequencing, selections, and loops. In this environment, coding blocks like parameterized move and turn blocks can be used to program the movement of a character to a two-dimensional space that contains obstacles, rewards, starting and finishing locations. A cool thing about the project is that students can create their customized grid using the characters in the menu and can share with others. Students with visual impairment and blindness who might have difficulty using the mouse may prefer to utilize the keyboard and to navigate to the workspace toolbox or grid. Therefore, the grid world supports different keyboard shortcuts to allow quick access to different environment functions. Screen readers often cannot provide specific information from the blocks-based languages and are not able to assist with many needs of a student with a visual impairment while programming. Speech synthesis interfaces are supported by most web browsers. The grid world uses the JavaScript speech synthesis API to provide audio feedback to the student based on specific contextual situations within the environment, such as describing the surrounding location of the current block selected in the code workspace, stating the block type selected in the palette, describing specific debugging information in the executable world, or describing grid contents and cube locations. Along with vocalized speech output, the environment also provides a variety of tones to acknowledge the actions and steps of the students in various contextual situations. Now let's move on to a previously prepared demo of the grid world to give you an insight of the functionality. The grid world. Here you can see a 5 into 5 grid that has been created with different characters. Students can also create their own grid by dragging and dropping different characters from the menu and then move a default character across the grid. The grid world has been developed keeping in mind both students with and without visual impairment. The workspace area has been created using Blockly. Our environment supports accessibility for students with visual impairment and blindness. It comes with a built-in screen reader and is also accessible by different shortcut keys and various fonts. Pressing the E key will enable the screen reader and keyboard accessibility. Then pressing the H key, one can go to the first cube of the grid. Pressing the arrow keys will take him from one cube to another. While moving, the cube location and containing characters will be read in order to acknowledge about different characters and their positions in the key.
1,1 contains overhead 0. 1,2 1,3 contains ghost. 2,3 contains apple.
The customer can be saved by pressing the G key. It can also be exported to a downloadable file. For exporting, one can press the X key and then can import by pressing the I key. The grid can also be cleared by pressing the U.
Exporting grid. Grid has been unsaved. Reload page to creating grid. Importing grid.
Let's create a code. Pressing the T key, one can navigate to the first block in the palette. Then pressing the W and S key, you can move upwards and downwards. Pressing the Enter key, the block will be dropped into the workspace. Connecting the blocks and moving from one block to another can also be done using the W key.
Move forward. Move backward. Move up. Move down. If half that I do an action, I'll do another action. Repeat 2 times, do a specific action. Repeat 2 times. 2 A. Move forward. Move backward. Move up. If fast. Ahead. 2 else. Move forward. Move forward. Move backward. Move down.
After creating the code, pressing the R key will run the code. While running, the executed blocks and location of the moving characters along with other characters will be read. For the debugging purpose, the execution can be paused and resumed by pressing the P key twice.
Run code. Move forward 1, 2. Move down 2, 2. Move forward 2, 3. Apple. Code crossed. Code resumed. Move forward 2, 4. Move forward 2, 5. Lollipop. Move down 3, 5.
Like the grid, the workspace can also be exported and imported using the O and M keys.
Exporting code. Project browser. Button. Close dialog. Button. Close the dialog.
It can also be saved by pressing the B key.
Workspace saved.
Some of the functionality in the grid bar still requires the use of a mouse. We will try to replace them by shortcut keys and make it more accessible to visually impaired and blind users. That's all for now. Thank you. This project will be tested and evaluated through several empirical studies. As a first effort, due to the unavoidable pandemic situation, adult sighted students will be recruited for performing the study. And then once everything gets back to normal, to perform the main study, sighted children will be recruited from summer camps, and students with visual impairment and blindness will also be recruited through our contacts at our state school for the blind. To perform the study and train the students, a sequence of lesson plans will be developed. After each study, the environment will be improved based on the collected feedback and questionnaires from the participants. We hope the broader impacts of this work will result in advanced capabilities that broaden participation in computing by enabling children with visual impairments to participate fully in computer science education opportunities. So yeah, that's all for now. Thank you.